To discuss about one simple topic, stability analysis using RH method, Routh-Hurwitz method. Stability analysis using RH method, Routh-Hurwitz method. So this method is used to find the stability of closed loop system. The stability of closed loop system, before going to find the stability of closed loop system, we have to know the transfer function of closed loop system. The closed loop transfer function written C of s by R of s is G of s 1 plus G of s H of s, where G and H, where G is system transfer function, H is feedback transfer function. So to find the stability of a closed loop system, we need to write the characteristic equation first. First we have to write the characteristic equation. So the characteristic equation is nothing but 1 plus G of s H of s equal to 0, which is nothing but the denominator of the closed loop system. Normally the numerator of the transfer function is location of zeros, denominator is location of poles. So the characteristics equation gives the location of closed loop poles. The location of poles decides the stability of the system. When the poles lies left off of the S-plane, so assume this is the S-plane. S-plane is complex plane, real part and imaginary part. If poles are on left side, either axis, real axis, or left side, entire left side, then system is stable. If poles on right side, system unstable. So Routh-Hurwitz is one of the method used to find the location of closed loop system. So the stability is, we can say, stable system. System is either stable or unstable. If the poles on left and imaginary axis, then we can say it as a limitedly stable. So three categories: stable, unstable and limitedly or marginally stable. So limitedly marginally stable means some poles lying on imaginary axis and remaining on left of the S-plane. Okay. So now we are going to consider a simple example how to find the stability of closed loop system using Routh-Hurwitz method. Okay. So consider a simple transfer function G of s equal to 1 by s plus 1, 1 by s plus 2. It is nothing but open loop transfer function of the system. To find the stability, we need a characteristic equation. So first find the characteristic equation from the open loop system. So here the H of s is nothing but a feedback, so no need to so finally s plus 1, s plus 2 plus 1 equal to 0. So characteristic equation the denominator of closed loop system equal to 0. Characteristic equation. So now s square 3s plus 2 plus 1 equal to 0. Finally s square 3s plus 3 equal to 0. So characteristics equation of the given system. So using the characteristic equation s square 3s plus 3 equal to 0. Step 1, we have to construct Routh array. So Routh array construction is purely based on the order of the system. The first two rows of the Routh array constructed from the characteristic equation. So first two rows from the characteristic equation. The first row always start with the highest power of s and its corresponding powers. So highest power is here s power 2. It is an even number. So consider only even powers in this R1 row in R. So highest power is 1 2 s squared whose coefficient is 1, and next one is s power 0 whose coefficient is 3. Now you go second row, so that means s squared row, s squared 1 row, s power 0 row. So in the second row, odd power means we have to write s coefficient, s power coefficient 3, and afterwards no, so dash. So no value for in this row. So we have to complete the row up to s power 0. In s power 0 means you assume the value to be find out in this row is x. So how to find the value of x is, assume this is a1 and this value is a2 and b1 b2. So the formula to procedure to find x is, we consider the first two rows, first two columns. So by a1 a2 b1 b2. The procedure is multiply first and multiply second and divide by the first element second row, first element third step. So b1 a2 minus a1 b2 divided by b1. So substitute the values and find what is the x1 x. So b1 is 3, a2 3 minus a1 1, b2 0, then b1 value is 3. So final answer is, what we get is 3, x is 3. Okay. So the values in first column 1 3 3. So all the first column elements are positive. All the first column elements positive. So if positive means system is stable. How many roots? 2 roots. Therefore all the 2 lying on left half of S plane. That's all. So this is the conclusion about stability of system. So final conclusion is, no negative element in first column of route array. After inspection, inspect the first column of route array. No negative elements, no negative elements, therefore system is stable. So this is a very simple application or simple procedure to find stability of closed loop system using route array. Actually, in this problem, the given transfer function is open loop. So when the system open loop is given, system given is open loop, but we are finding stability of closed loop. So RH method can also be used to find the stability of closed loop system when the open loop system alone is given. Okay, this is another one. Okay, now I hope everyone is clear. What is stability? System roots lying left off of the S-plane means then the system is stable. If any pole on right side, then the system is unstable. If poles on both left side and imaginary axis, then it is called limitedly or marginally stable. So to find the to use RH method, we need characteristic equation. How to find characteristic equation means first write the transfer function of closed loop system. Afterwards, equate the denominator to 0. 1 plus g of s h of s equal to 0. Then it is called characteristic equation. So we used one example, simple example. The g of s equal to 1 by s plus 1 into s plus 2, which is a open loop transfer function. So first we have to find the characteristic equation. After finding the characteristic equation, route array starting from the highest step to last power. If the highest power is, here the highest power is 2, therefore 2, 1 and 0. In case the highest power is s power 6, for example, I'm saying for example, highest power is 6, then we have to construct s power 5, s power 6, x power 5 from the problem statement. Then s power 4, s power 3, s power 2 rows we have to calculate. S power 1, s power 0. After calculation, check the first column. If first column elements are positive, then system is stable. If any one is negative, system is unstable. Okay. So after calculation, find the inspect the first column. All the elements are positive, then the system is stable, which means that all the two poles, two roots lying left half of the S-plane. Okay, then hello students. Now we are going to find magnitude and phase angle of now we are going to find magnitude and phase angle of given transfer function. So how to find magnitude and phase angle? Assume the given transfer function is in the form of s plus 1, s plus 2 divided by s plus 3 and s plus 4. To find the magnitude and phase angle, first put s equal to j omega, then g of j omega equal to j omega plus 1, j omega plus 2 divided by j omega plus 3 divided by j omega plus 4. So the given is in the complex form. So we have to write a plus jb equal to root of a square plus b square, then tan inverse b by a. In this form we have to write first. So for the first term, j omega plus 1 square root of 1 plus omega square tan inverse omega. For the second term, 4 plus omega square tan inverse omega by 2. Then in the denominator first term, square root of 3 squared 9 plus omega squared tan inverse omega by 3. In the second term of the denominator, root of 16 plus omega square, then tan inverse b omega a is 4. So after substituting this value, we have to write only magnitude and only phase angle separately. So in this expression, the blue color what I circled in the numerator and denominator are magnitude of g of j omega. So the magnitude of g of j omega equal to numerator a square plus b square for the first term. So a is 1 plus omega square. Then for the second term, a is 2, b is omega. So b plus omega square. For the denominator first term, a is 9, b is omega. So 9 plus omega square. Then in the fourth term, it is a 60 plus omega square. Okay. So this is the expression for magnitude of j of j omega. Now phase angle means phase angle of g of j omega depends. We have to add the values, the magnitude phase values in numerator and denominators. So what I circled in the numerator phase values, we have to add both, and the denominator phase value underlined in the green color subtract with the numerator value. So which gives the resultant phase angle. So numerator tan inverse omega minus tan inverse omega by 2 plus, then it is subtracted with denominator values tan inverse omega by 3 minus tan inverse omega by 4. So these two are the expressions for magnitude and phase. So by substituting various values for omega, we can easily find out the phase angle and magnitude. By plotting this value, so we can identify what is the phase crossover frequency, gain crossover frequency, phase margin and gain margin. That's all. So this is the simple procedure to find magnitude and phase angle. So substitute put in the for the given transfer function, put s equal to j omega, then split magnitude and phase angle, write phase magnitude separately, phase separately. So simplest procedure to find out magnitude and phase of given system.